Welcome to AWR University Videos. The topic of this lecture is transmission line, and more specifically, I'll be talking about the circuit representation of a transmission line. Now, to understand transmission lines, we really need to start with the electromagnetic fields. Many people feel like the boy and girl at the top of the screen when it comes to E&M, a little confused or concerned. But a fun fact is that electrical engineers have a hard time with E&M just like students. And it's all okay because we all have a university professor like the one pictured below to help us through the course. The equations shown on the right are Maxwell's differential equations, which are the basis for electromagnetism. And even though it might be a very challenging concept, electromagnetism is the physics behind circuits, therefore very important to understand. It describes transmission lines, antennas, and it is the basis of circuit theory because circuit theory is derived from electromagnetics. However, there are some exceptions, such as the lightsaber. In theory, it is electromagnetic, but it actually goes against the physics that magnetic field has no beginning or end. Or maybe Jedis are just powerful that they can just defy physics. And devices like you see here are mainly described by quantum mechanics. Black holes are described by physics like general relativity. But for electrical engineers, we'll be working with electromagnetics most of the time. Physically, a transmission line is a material that provides a link from one location to another. In circuit theory, we analyze how the transmission line transmits electromagnetic waves. Two examples of transmission lines that are fairly common are power lines and underground telephone wires. Power lines are transmission lines sending low-frequency electromagnetic power from power plants to distribution stations. Underground telephone wires are coaxial lines carrying telephone conversations of high-frequency electromagnetic waves. Now I will show you how to create a transmission line in Microwave Office. I will be using the standard measurements from an RG58 cable for the inner and outer diameter of this transmission line. Okay, here we are in Microwave Office now, and the first thing I'm going to do is create a new schematic so we can start building our circuit. So I'll go up here to the toolbar and I'll click on this schematic option, and I'm going to call it coax cable, and then click OK. Now right now I'm under project settings and I would like to change that to elements. So click right there, and then I'm going to go up here to pick my transmission line on the plus sign, and then once again on coaxial and physical. And I'm going to just pick the first option right here. And now I would like to add a source. And I'm going to choose a signal source and this V plus one. And I would like to use this one so that I can see the change in the frequency over time. And lastly, I need a load, so I'll go up to lumped elements and to resistor, and the very first one is the load. And drop and click. And I would like to use the 50 ohm load so that the transmission line of the RG58 cable, which is also 50 ohms, will be the same as the load, so I can have Z out equal to Z in. Now I'm going to connect my wires and add ground. So go up here to the toolbar to click on ground and add one there and two more. And now I'm going to add some values. So for my voltage source, I'm just going to have an amplitude of 1. I'm going to have the width of 4 nanoseconds, a rise of 1 nanosecond, and a fall of 1 nanosecond. And for my coax cable, as we know from the standard RG58, inner diameter will be 0.9 millimeters. The outer diameter is 2.95 millimeters. And I would like to start with a length of 1,000 millimeters. One too many, sorry. And my ER will be 2.0 27. And I'm going to change my row to 0. Now one more thing we have to do is to go to Project and go to Project Options, and we'll right click and say Edit. And I would like my frequency to just be at 0.1, and it's just going to be that single point. And I need to click Apply, and you can see right here that I have my 0.1 in just one of them, and then OK. And I have my units in millimeters, which is what I wanted, but in case you wanted to use meters, you would just go to Options, Project Options, Global Units, and then you can change from frequency of megahertz to gigahertz, or you can change meters to millimeters. But I'm just going to stick with millimeters for right now. And OK. Now in order to see what we've done, we need to create a graph. So right next to the schematic option is an Add New Graph option. So we'll click that, and we'll call it Coax Cable Graph. Oops, sorry, spelled that wrong. There we go. And I would like it to be rectangular. Now OK. And to add new measurement, we're going to right click on the graph and scroll down to Add New Measurement. And for a measurement type, it's nonlinear voltage. And for measurement, it's going to be voltage in time. And our data source, we want to make sure it's under coaxial cable. We only have one option right now, but if we created more schematics, they would all be listed right here. And we're going to start with this voltage plus V1. Oops, my mistake. I forgot to add our ports. So I'm going to cancel out, go to coax cable, or probes, my mistake. So click here to the measurement probe right here, and then one more right here on this node. Because without the probes, we wouldn't be measuring any voltage. So kind of pointless. Once again, right click, add new measurement, and we want it nonlinear voltage. Oops, too far. There we go. V time, coaxial cable, and probe 1 first, and it's going to be under this applic trans, and hit apply. And then second, we want probe 2, and then apply, and OK. And now in order to see results, we go up here to the lightning bolt, and it says analyze, and click the lightning bolt. And here we can see from V time, which was our first probe, and how it has now been delayed about 5 seconds through the transmission line. And this is how to create your standard transmission line in Microwave Office. Most engineers do not like working with electromagnetic because of all the vectors and the partial differential equations and electric and magnetic fields. And wouldn't it just be a lot nicer if we could just work using currents and voltages? And we can do that now, except when we work with distributed elements, such as series inductance L per unit length, series resistance R per unit length, parallel capacitance C per unit length, and parallel conductance G per unit length. And a picture is shown below, so you have an idea of how they all look like in parallel and series. And in a few minutes, I'm going to show you how you can represent a transmission line in Microwave Office using these 4 elements. Kirchhoff's voltage and current laws derive from electromagnetic theory, but in order to do that, certain assumptions need to be made. Otherwise, we would just have circuit theory and we would not have electromagnetics. Now here are the 3 laws of the transmission line that we must obey if we can use circuit theory. Number 1. For our transmission line, we cannot have too high of a frequency because when you study the electromagnetic, we are assuming there is something called TEM mode, When you go to a higher frequency, more modes will propagate. And if that's the case, you cannot usually use circuit theory. Fortunately for normal circuits, this isn't a problem. Number 2, we need to have two conductors. One is a signal, the other is the ground return, and the current goes out on the signal wire and back on the ground wire. For example, if we have a coax cable, like the one pictured below, you can clearly see the two conductors. The current goes down the middle line and returns on the inner side of the outer conductor. It returns this way because of the skin effect, which is something that we'll go into later. And usually the outer conductor is called the ground. Now, for our final assumption is that there is only one dielectric material everywhere. For our coax line, that is true. Typically, they use a plastic material, but for power lines, they may use air and even a vacuum. Sometimes we can use circuit theory for transmission lines even when it is not strictly TEM mode. The most classic example for circuit designers is something called a microstrip line. And the problem here is that you have your dielectric and two conductors, but you also have air above. So really you have two different materials acting as the dielectric, the air and the board material. So it's really called a quasi-TEM mode, and that will degrade the performance at high frequency. But today we're just going to stick with the coax line and a perfect transmission line. We said we wanted to look at a circuit model of a transmission line and not have to work with the electromagnetic concepts. So let's see how we can do that. In circuit class, you learned that if you have two different conductors and you put a voltage between them, you have a capacitance. That will be charged on the inner surface of the outer and charged on the outer surface of the inner, creating a capacitance between them. Now the question is, how much capacitance is there? It depends on how long the line is, and we can use capacitance per unit length equation to find it. In order to find the capacitance equation, we have to solve Maxwell's equation, but we're not going to do that today. Today we're just going to use the measurements from a standard RG58 cable. And as you see below, we found that capacitance per unit length is 95.92 picohenries per meter. We have a current on the conductors, and in particular, if you have a current, you're going to have a magnetic field. And from this picture, you see the magnetic field goes around the inner conductor and returns on the inside of the outer conductor. If you have a current and it generates a magnetic field, you have an inductance. And inductance is defined as the ratio of the current to the flux. And flux is the magnetic field going through the surface. For us, instead of flux per unit length, it will be inductance per unit length. Here are the standard equations for inductance, and here's the value that we get with the standard RG58 cable, 0.2398 microhenries per meter. Conductors are not perfect, and normally an RG58 cable is made out of copper, while cheaper transmission lines might be made out of aluminum, and expensive lines might have silver plating. But regardless, it is never a perfect conductor, so there is always resistance. So the conductor heats up and leads to power loss. So now we must include the resistance in our model, a resistance per unit length. The longer the line, the more resistance in the line. However, there is a slight problem because there are resistance from both conductors, the inner and the outer. Therefore, our resistance model must include the losses of both conductors. We are cheating a little bit because if we have loss, then it is not perfect TEM mode, but it is sufficient for everyday engineers. I just wanted to remind you that it is now no longer in perfect TEM mode. Here is the formula for resistance per unit length. The final effect we need to consider is that the dielectric might not be a perfect dielectric. It could conduct current going between the two conductors. Imagine a line that is filled with the dielectric of water. The line will be shorted out because there will be a current flowing through the water from the inner conductor to the outer conductor. What we can do is model the conduction of this dielectric as a resistor between the two conductors. We call it conductance, which is just 1 over resistance, because the resistance in the model is going to be parallel with the two wires. And in circuit theory, it is easier to talk about conductance rather than resistance when adding up the values. Also, the nice thing calling it conductance is we will not confuse it with resistance, which is due to the imperfect conductors on the line. And here are the standard formulas for conductance of the line. Now for our first example in Microwave Office, we're going to assume that the line is perfect and there is no loss, meaning no resistance and no conductance. And we're going to use the RG58 coax line dimensions, which is a standard 50 ohm line that you normally see around in your house. The inner diameter will be 0.9 millimeters, outer diameter 2.95 millimeters, relative permittivity 2.027, and a length of 1,000 millimeters. Now we're going to make a transmission line using the capacitance value that we found and inductance value. So let's go to create a new schematic, RLGC, but only LC. And let us add some elements. So we'll start with our load at the very end, and also our source, just the same as before, the pulse. And lastly, the transmission line we're going to be using is called RLGC, and we're going to grab the RLGC TX. And notice here how you can insert your own values for R, L, G, and C, but we will be using the same ones as the RG58 cable. And now we'll connect the two nodes and add a ground. And we'll use the same value as before to keep it consistent. So 100 milliliters in length and a frequency of 0.2 gigahertz, a resistance of 0, an inductance of 0.2398, 0, oops, I missed a bracket, 0 conductance, and a capacitance of 95.92 picofarads. And if I was wanting to change the units that were on here, for instance use meters instead of millimeters, I would go to Options, Project Options, Global Units, and I can change that. Now let's add a test probe, and one more here. And now we're ready to graph it. So we'll add a new graph, and we'll call this one RLGC only LC graph. Like before, we'll right-click, add new measurement. It's going to be voltage, V time, and instead of using coaxial cable, the probes from the coaxial cable schematic, we're going to use the RLGC only LC. And then probe 1. And this time we're going to have it in H-spice strands. Apply, and we'll do the same for probe 2, and apply again, and then OK. And now let's see what happens. So it looks a little familiar. It looks the same as this coax one. In order to get a better view, you can close these two tabs, and then Window, Horizontal. And you can see that they're pretty much the same. So this way, we know that we can also represent our transmission line coaxial cable using our own values that we found for R, oops, not for R, sorry, for L and for C. Here is the equivalent circuit of the RLGC transmission line that we used in Microwave Office. And now to conclude our lecture, we'll go over a few main points of the video. First, that electromagnetics is the physics behind circuits. Transmission lines can be represented using distributed elements, such as the inductance per unit length, resistance per unit length, capacitance per unit length, and conductance per unit length. And that there are three assumptions of a transmission line in order to apply circuit theory. First, that for the transmission line there cannot be too high of a frequency, that the line needs to have two conductors, and that there can only be one dielectric material. Capacitance is the charge created from the inner surface of the outer conductor and the outer surface of the inner conductor. Inductance is the ratio of the current to the flux. Resistance is loss from the conductors. And conductance is the loss between the two conductors. And as I showed you in Microwave Office, it is possible to represent a transmission line using an equivalent circuit. Thank you very much, and that concludes this AWR University video.